We're going to shift gears. Today, we've been talking about finite difference so far, and now we're going to switch over to what are called spectral methods. And in some sense, spectral methods are basically going to be based on the Fast Fourier Transform, which we've already talked about, which is already going to be part of your homework. But in some sense, these spectral methods are a more general class of solving problems. The idea is they call it spectral methods because you basically switch from looking at the solution in the regular domain that you're looking in, for instance, in time or space. So, if you have something you're looking at in space, and what we've been doing so far is saying, okay, let's just chop this up into a bunch of points. And when we think about evolving this with derivatives and so forth, we say, okay, take this point, and it depends upon its neighbors. So whenever we approximate the solution to this thing, we're really doing sort of a local approximation. This point relies on what's going on in its neighborhood. It only sees the effect of things way over here because the next point lies on this thing and put the next point on its neighborhood all the way across. And so it connects them all together through a chain through this big matrix A. So this is not directly connected to this, but sort of indirectly. Okay? But for the most part, your approximation then can be considered local. I care only about my neighbors. So that's what the finite difference does, and it's based completely on these Taylor expansions. Now what we're going to talk about is the spectral method, which is instead of characterizing things on local expansions, we're going to do what are called basically global expansions. Instead of expanding with Taylor series, what we're going to do is expand in terms of cosines and sines, which are actually global functions over the whole range you're looking at. Okay? Now we've already defined a Fast Fourier Transform pair, or a Fourier Transform pair. Let me do it again here. Fourier Transform is nothing more than you shift it over. Here's one possible definition of the Fourier Transform. And in all the definitions out there, the only difference is sort of in terms of where you put the 2 pi and where if you have that minus or plus. Okay? So there's your Fast Fourier Transform pair. If you take a function, you want to transform it, all you have to do is multiply that e negative ikx, integrate from negative infinity to infinity. What you've essentially done is now e to the ikx is nothing more than sines and cosines. So what you're basically doing is projecting this function onto this oscillatory behavior. Okay? Rooted in Fourier series, or the idea of Fourier, which has said, look, I can take any function you give me, and I can represent that function as a sum of cosines and sines. That's essentially what this is. But now, you're integrating over the whole space and writing terms of things in terms of f of k. So in other words, it's in the wave number space. In other words, e to the ikx, this is like cosine kx. Well, what does k control? The frequency. So you're integrating, basically writing everything now in terms of a sum, this infinite continuum of frequencies. Okay? And then when you want to come back out from this Fourier domain, which is in frequency space, that's why we call it spectral space. Spectrum usually refers to the frequency components. You just multiply by now positive e to the ikx, integrate over all possible frequency components, and you get back out your function in the space domain. So this transformation really does take you away from this picture here, where you're saying, I'm looking at this thing as a function of x. Now you're saying, if I Fourier transform, I'm going to go look at this thing as a function of frequency, whatever it may look like. And I'm going to do all my manipulation in terms of this thing in the frequency space, and then when I'm done with it, then I'm going to go back. Okay? Now the big idea for Fourier transforms was simply rooted in what happens to the derivative, the Fourier transform of a derivative. And we derived this in class using chain rule, which is, if I take the Fourier transform of the nth derivative of a function, I simply get I, k to the nth power Fourier transform of the function. This is what allowed us then to start thinking about, hey, I could solve problems with this now. Because now this gives me this specific relationship between how derivatives and the function itself interact in a very simple manner. I can use this now to solve almost anything I want. Okay? It's no different than when you did finite difference. The key there with Taylor series is it gave you a relationship between how this point you're trying to solve for relates to its neighbors. Once you have that, you can write down this big matrix A, for instance, that does differentiation. And here, this is the equivalent expression. Okay? Questions? Everybody good? All right. Now, the big deal here is that this is on an interval negative infinity and infinity. But we know that on the computer, you're never going to have negative infinity to infinity. You're always going to have to work on a finite domain. It can be large, but it has to be finite. Homework 1, infinity was like 2. Okay? And that was a pretty good approximation. So what infinity means is kind of relative, but you have to work on a finite domain. And so when you go to a finite domain, the definition of the Fourier transform changes. And in fact, now when you go to a finite domain, you actually get the following definitions of the Fourier transform. And in fact, these are the definitions right out of MATLAB. If you look at the help, you go help FFT, this is what will pop up. Let me write it down. And this is the Fourier transform pair out of MATLAB. And generically, most algorithms give you this. Okay, so this is for k between 1 and n, and this is for n between 1 and big N. So here's basically what happens is, now that we go to a finite domain, two things happen. First, this integral becomes a sum. Because now we're only going to add up certain frequency components. Which frequency components? We'll talk about that in just a second. And also, our box size is now going to be limited. In fact, what we've done here is we've taken a box size of size 2 pi. We've scaled the whole problem down. Whatever your domain happens to be, boom, shrink it down to 2 pi. That's when these guys are periodic. These are nothing more than cosines and sines. We're going to shrink everything down to 2 pi and then work on that interval. Okay? So that's the fundamental period. Now, if you remember from what we did in class, remember how we defined our k vector? The k vector had this 2 pi over L times, and then I constructed the vector. This is just rescaling down to 2 pi. Okay, so let's talk about actually what this means in terms of what we're going to expand in. We're going to be expanding now on a domain of size 2 pi. And our basic function is this e to the I 2 pi k minus 1 n minus 1 over n. Now, if you were to write out the first few modes of this thing, okay, for different k and n values, what you'd find the basic solutions are, this thing here is nothing more than, what is it? It's cosine of 2 pi k minus 1 n minus 1 over n plus I sine 2 pi k minus 1 n minus 1 n. So for instance, what if I pick k to be 1, n to be 1? What do I get here? Well, sine of 0, and there's an x. But x would be good there. Okay. Well, sine of 0 drops out. What's cosine of 0? Constant. It's 1. So it's one of my basis functions. And then I can build up different basis functions from here. The next one's going to be a cosine that does this, a sine that does this. What does my sine want to do? It does this. All these functions are generated from picking different integers here. And the whole idea is I can say, on a domain of 2 pi, I take any function, and I'm going to add up these functions together in a certain way to represent that. Okay? The only thing I need to know then is what are the coefficients? How do I add them up to get these right? So if I take a generic function on an interval 0 to 2 pi, my claim is that function there is nothing more than a sum of cosines and sines. And all I have to do is figure out how do I weight them correctly. How much of this one, how much of that one, how much of this one do I add up? That's the whole process of Fourier transform. And the weighting of these things is given by these coefficients here. Okay? So that's really what the process of the Fourier transform does, is it basically says, look, let's go ahead and expand in terms of these basis functions. The only thing I've got to figure out is how much do I add of each basis function? How much cosine of 1x, how much cosine of 2x, how much cosine of 3x? And the reason now that you're actually working with finite sum is because now you are not allowing things like, how about if I do a cosine that looks like this? You only want periodic solutions that are periodic over 2 pi. This is not periodic. It's not an allowed function. There's only going to be a finite number of values here for n and for these guys that are going to allow things to fit in this box. Okay? Now, in addition to the Fourier transform, the generic Fourier transform, which is this complex piece here, you could also say, well, suppose I actually want to think about maybe doing a cosine transform or sine transform. What if I just want to keep one or the other? Because you can do this. Okay? Now, when you do that, what you're essentially doing is saying, okay, if I want to do a cosine transform, which, by the way, in MATLAB is dct of some vector, discrete cosine transform. It used to be that dct used to be in your standard package. It's no longer there. It's part of one of the toolboxes, I believe, the optimization or signal processing. So they've shipped it off. But what it did is said, okay, how about allow your solution to just be written as a sum of cosines. This is what the discrete cosine transform allowed you to do. And what the discrete cosine transform algorithm did for you is essentially calculate all these A of n's. Now, the price you pay in doing it, this is the key for Fourier transforms, is how long does it take you to calculate these A of n's? Or, if you come back to the regular Fourier transform, how long does it take you to calculate these things? Here. At first sight, at first glance, let's talk about it. I have to do this sum from 1 to n. for every single k value. And there's n of them. So for every n value, you have to do n operations. If you add this all up, on the surface it looks like it costs you this much to do a Fourier transform. And so that's the price you pay if you were to just generically do something like this. The point is, and what we're going to talk about sort of in the second half as we get along in here, is that the fast Fourier transform allows you to actually calculate those things n log n. Okay? But at least on the surface, it looks like this. We'll talk about what goes like, makes it go like that. All right. So back here. So now cosine transform will do something like this. And in fact, let's look at what some of the modes of this thing might look like. So basically, you're doing is going to do an expansion in terms of these cosines. And here's what they look like. Here's the first one. So half a cosine period. Oh, sorry. The first one is this. Just a constant cosine of 0x. The next one is like that. The next one, like this. And you see there's this whole hierarchy of cosines that you can put up here. Now, interestingly enough, take a look at these functions here. What kind of boundaries do they have? So if you look at this, you're starting off at 1. It's between, sometimes it's -1 and then 1, -1. It switches between these two, big deal. But the important thing is, what's the slope here on all of it? For all of this, for the discrete cosine transform, you have that the derivative is 0. So, one of the reasons you might want to use the cosine transform is if you have a problem whose boundary conditions are that at the boundaries the derivative is 0. Because, in fact, this thing automatically satisfies that, which is perfect. So if you want to take a function and you have these boundary conditions for your problem that are of this type, you would just say, use a discrete cosine transform. Because it automatically satisfies the boundary conditions, so I can just take any generic data and expand it out in terms of these things, and it satisfies it. Yeah.
Cosine is not periodic over 2 pi, is it?
No, it's not. So it's a little bit different expansion than I wrote down here. So now it's for you can still do this with basically the way the cosine transform works it with half periods. And then it allows you to go, and then the next one, instead of doing this, it's like that, and so forth. So this is kind of nice. So it's something to keep in mind. Generically, what we're going to use is the fast Fourier transform. One, because it's in MATLAB. We don't have to use a toolbox, which is ridiculous that we have to get this through a toolbox. But, and two, these are very specific boundary conditions, and a lot of stuff we're doing doesn't have that boundary condition. So, okay, so that's the cosine transform. Now, let's talk about the sine transform. So what the sine transform does is something very similar. The basic idea is to say, okay, for the sine transform, it's DST. Discrete sine transform. And what it does, same kind of thing. Now you're expanding in terms of sines. Again, half periods allowed. So there would be your first one, your second mode, third mode, and so forth. Okay? And what do you notice about the boundaries here? The boundaries here, sine is always 0, 0, and 2 pi. So basically you're saying, okay, for something like this, I'm basically working with functions that are pinned at the boundaries. So if you have a problem where you're pinning things, this might be the appropriate thing to use. So the discrete sine transform, pin boundaries. Discrete cosine transform, cosine expansion with zero boundary conditions, zero derivative boundary conditions. And then finally, this one here, which is the generic Fourier transform, which expands in terms of both sines and cosines, periodic boundary conditions. Okay? So those are your three flavors of spectral transforms that you've got, or that we're going to consider. Okay? Now, I'm going to make a comment again. When you take a generic function like this, remember, with this, when you're using your finite difference discretization, you take a point, and what it cares about are its neighbors. It's local approximation. Notice the difference here. When you do this thing here, it says, take this whole thing, any point, you want to solve, you want to know what the value is at that point right there, or its derivative? What you've got to do is add up a bunch of cosines and sines that expand over the whole interval. It's like a global approximation. Okay? What it does is it doesn't say, all I care about is what's going on in my neighbors. No. What it does is it says, actually, if I want this point here, I've got to add up a bunch of functions that are valid over the whole domain I'm working on. So it's like a global function. So it makes it very different. And it's one of the great things about spectral methods. Accuracy is has exponent. It's called accuracy beyond all orders, exponential accuracy. So when you do finite difference here, order delta t squared, your error goes like order delta t squared. Basically, when you do a Fourier spectral expansion like this, like Fourier methods, is beyond any algebraic power of accuracy. So the accuracy is amazing in comparison to finite difference methods. Okay? So there's two really big wins here. One, accuracy. Two is speed. Because what we're going to talk about is this algorithm takes this operation count from order n squared down to n log n. And order n squared is about as fast as you're going to do it for if you discretize, right, and you write a big AX equal to B matrix solve problem. That's as fast as you're going to really be able to get as order n squared guaranteed. And here, n log n. So pretty much, if you can use spectral methods, you do. That's a generic rule. All right? Always use it if you can. Okay. So, now let's start on the theoretical ideas of what goes on with this spectral transform. So, let me erase this stuff. All right. So here we go. Now we're going to move towards understanding the fast Fourier transform. So the fast Fourier, so far all we've talked about is generic properties of Fourier transform, and now we're going to talk about what brings it down to n log n. And mostly what I'm going to do is sketch for you the idea. I've given some references in there if you want to go. It just takes a long time to actually work everything out. So I'm going to highlight for you the results, okay? Versus actually bore you with them. You may be bored anyway, but at least it'll only be bored for 20 minutes as opposed to 3 lectures. Okay. All right, the fast Fourier transform. Here's the observation. If you remember in my definition of the fast Fourier transform, for instance, from MATLAB you get something like this. So this piece here is the key. It's the oscillatory, it's the expansion part. It's the cosines and sines. Carries all the information. So one of the things you can notice from this is I can actually write this then as f of k. And I can take this piece here, and I can write it as omega and k, where the omega and k is just this exponential. So really, in the end, you can say, well, okay, so if I want the whole function that I'm looking at, this is just one component, that kth component. If I want the whole vector of it, I have to sum over all of these. I get something like this. So this is the idea. So you're really working with, this is the basis expansion piece, the function right there. Okay? You're trying to calculate this piece. This piece here is already known, but these are the important basis functions. And these are how long is it going to take me to calculate that? That's what you need for a given function. Okay. So the way the FFT works. Cooley and Tukey are the guys. They came up with this algorithm for doing it. Again, we'll basically summarize it. So they came up with this algorithm somewhere in the mid-60s, and it really revolutionized things. Partly because at this point in history, if you did anything, it's going to cost you order n squared. Guaranteed. All of a sudden, they came up with this algorithm. First time you drop something down, order n log n. That's an amazing improvement in speed. Put yourself in the 60s. Well, I was in the late 60s anyway, 68. I just made the cutoff, not too far. But if you put yourself back then and you look at computational power, okay? Computational power, what did they have for computers back then? Well, pretty much things that took up a whole room, right? The invention of the computer was 50s. And you had about 15 years of things going on. Even the simple ODE solve that we did in class for homework 1, for instance, shooting across once. How long would that take you to do on a computer in 1968? How long would your homework 1 take to do just part A on the computer? You're talking about days. Your computer now just goes, right, cranked it out in less than a minute, often. You're talking days of work, okay? So if you can get a scheme that drops from order n squared down to n log n, huge savings then, because you're just so much slower. Now, even if you're using the slowest thing out there, okay, so I wait 2 minutes instead of 1, oftentimes, for a lot of problems, okay? But then, this was a huge improvement. And so, for them, coming up with this algorithm, they did it just simply to try to figure out, hey, is there any way to make this faster? It wasn't like they were trying to do math research. They were working at a company. I believe they were at IBM, perhaps. And so they were trying to figure out a better way to do this. So here's the idea. Consider this matrix here, the matrix f of n, which is an n by n matrix. Uh-oh, I'm already boring you. Dang, I was hoping at least get past the hour, and good thing it's only 20 minutes of this stuff. Boy, I'd put you to sleep otherwise. But this is a matrix. And essentially what this is going to be equivalent somehow to our A matrix before. Our A matrix did all the differentiation. And now this f of n matrix is going to have all our Fourier components in it. And it's going to calculate these Fourier coefficients by doing a solve. We have to solve an ax equal b problem. Okay? Now, what are the components of this matrix? The ith row, jth column, has this in it, which I will rewrite in a little bit simplified form from before as this. Fourier coefficient, or oscillatory piece there, e to the I, j through kth column. So this thing fills out this matrix which has all these frequencies in it. Okay, and the size of the matrix n, by the way, determines the highest frequency you want to consider. When you have to cut off this expansion at some point, right? You say, I'm expanding cosines. Well, you could, in theory, you could expand from cosine of n pi x, where n goes from 0 to infinity. Well, in practice, you have to cut it off at some point. This determines your matrix size. Okay? So this is the expansion. Now, here's the key observation that's going to make everything work for us in what follows. The key observation is this. That. It's actually a very simple observation to make. What is omega to the 2n squared? Well, that is e to the I 2 pi. And here I'm just letting j and k float around for now. So I could put jk's on these things, but on the bottom I have 2n, because it's the 2nth component, and then e to the I 2 pi 2n jk. But there's 2n of those, so there's half of that one, half of that one. That is equal to the e to the I 2 pi n j k. There's a full one, but that's just, again. So really, this is like a simple observation that we have here. The consequence of this, however, is enormous. I even use that exact word, I think, in my notes. It's very far-reaching. What it says is there's this very fundamental relationship between elements of this matrix. Okay? So as you go down, as you start going down these matrix components, a lot of the matrix components are related to each other through this formula. Okay? One's the square of the other. So, here's what it allows you to do. And again, I'm not going to go into detail of it, so I'm going to sketch over it. Hope you'll be okay with that. I'm just going to give you highlights. This is like Sports Center or Math Center. You know, not Sports Center, but math. I don't want to say Math Center. I want it to be like cool Math Center. We have logos and everything. I could be up there to do, you know, last night's action. Here it is. So here's what happens. The consequence of this. The consequence is the following. When you have this matrix problem, to solve for your Fourier components, the coefficients of each, you know, expansion piece, you have to solve something that looks like this. Here is your ax equal to b. Okay, so this is your x equal to b piece. X contains all my Fourier coefficients. My y is what the function I'm expanding actually is, and this is your basis functions. So essentially what this results in is trying to, you know, do a representation like this and solve for these components. It results in a big ax equal to b. Now, order n squared operations. But because of that fundamental relationship, it turns out you can split this problem up to two pieces. And it's all due to this relationship holding. And what happens then is you can say, okay, let's split it up into what is called an even part, where what I do is take every other component, an odd part, every other component as well. Okay? Total of n components. And it turns out that that system that we wrote down there can be written then as basically 2 decoupled systems, where basically here's the relationship. The relationship holds because this is now f of m, where m is n over 2. It's half the size. And what allows us to do this is because of this relationship between the Fourier modes, this f of m basically is related to f of n in such a way that now we can basically take the problem, break it up into 2 pieces. Now, look at your operation count. To solve one problem, this one over here, cost you order n squared, because that's the size of this matrix. How much does it cost you to do this now? Over here, you've broken it up to 2 problems. Well, this one here is order m. So this is, or sorry, it's size m, so it's order m squared. But what's m squared? It's n over 2. Right? So each one of these problems is something like this, but I have 2 of them now. So I have 2 times this, so if you have 2 times that, you get order n squared over 2. So you see, in this simple procedure, going from here, which costs you order n squared, to here, which is 2 problems, half the size of it, each one, I just cut my work in half. Okay. The key question is, though, can I, from these 2 separate problems, how do I get back to my original problem? Because once I solve for these right, I've got to figure out how do I put it back into my original solution. And this is where a lot of algebra comes in, and this is why I'm skipping it. You find the following. The relationship back to the original problem is that your y components, which is what you're getting, the y components, the first 1 through n over 2 minus 1 of them are given by, you take this even part, add it to this coefficient times y naught, 0. And then and now you get the other half of them are given by n over 2 minus 1. Here's the other half. So you see what happens is to get back all your components, you're adding these and then you're subtracting these. And notice how it separates it. First n components, the first n over 2 components, next n over 2 components. And by the way, this is the genesis for this. Takes these problems, splits them into 2, splits them into 2, splits them into 2. This is what's going to happen next, which is this is a generic algorithm for basically taking this problem and breaking it down into 2 smaller problems. But notice, did we use anything specific here about this f of n? We said there's a very specific relation between f of n and f of m, where this is, if you use the fact that this thing had this structure where you square one, you get back to the other one, so that there's a specific relationship between f of n and this. But now we can just take these problems and split them up. Why not? Because now this is f of n. You can imagine there's a nice relationship between f of n over 2 to f of n over 4, a matrix of half its size. And then you can imagine it keeps going down to fn over 8 and so forth. In fact, this is the cascade that makes the whole Fourier transform work. You take a big problem, you split it into two. Half the work. Now, I'm going to take this problem here that we just did, I'm going to split it into two again. How much work? That's going to half the work again. So now, if I do that, it's going to give me order n squared over 4 is my operation count. I split it in half again. N squared over 8. This is why you want to use 2 to the n Fourier modes, because you keep splitting it in half and half and half until you can't split it anymore. Until this becomes f of n over n. And then what ends up here, this is just a 1-by-1 problem. You can't go any further down than that. One equation, one unknown. So we started off with n equations, n unknowns. We split it into two problems of n over 2 equations, n over 2 unknowns, but two problems of it. And then we split that problem to 4 problems of size n over 4. And then we split that into 8 problems of size n over 8, all the way down to n problems of size 1 by 1. And when you do this, the ultimate thing as you reach is n log n in that algorithmic structure. So what you do is you solve the 1 by 1 problems, and then you just follow these formulas all the way back up to write down your solution. Did I make that so clear? It's just, yeah. I always love this lecture because if you really want to get into the heart of this, it takes a long time, but I'm just skimming the surface just to give you an idea. Okay, and hopefully that's okay. It's okay with me. So ultimately, I think that's all that matters. All right. So graphically, let me show you what happens in this. Let's take a problem where I take n equal to 8. And I've shown you this classic picture on there. You start off with a collection of points. That you're trying to solve for. 8 of them, let's say. Because it has to be some factor of 2. This is 2 to the 3. And what do? We're going to break it up into 2 problems. Well, how did the two problems map over? Well, look at right here. This is how they map over. The first n of them, the first n over 2, the next n over 2. And they do so in such a way that the even and odd map over in sort of this fashion. They crisscross. Notice this is a problem 8 by 8. Now you've broken it down to a problem. Notice that these 4 are going to be now one problem. These 4 are going to be another problem. You've broken the problem into 2 parts. 8 by 8 problem now down to a 4 by 4 and a 4 by 4. Now, this 4 by 4 problem can be broken up into 2 by 2s. So what happens is you do the crisscross here. This 4 by 4 can be done the same thing. You break it up into 2 2 by 2s. This 2 by 2 can be broken up into two 1 by 1s. Two 1 by 1s. Two 1 by 1s. And two 1 by 1s. So this is often called the butterfly scheme in the literature. And what it does is you take it 8 by 8, two 4 by 4s, four 2 by 2s, eight 1 by 1s. Here's what's interesting. Take a bump like that. What happens to the points? Or maybe, so let's take this point right here. Where does it end up? If actually, hold on one second. Bad example. I just want to do this illustration. Where does y naught end up? Follow this path over here. When you break it down to these even odd problems, this point ends up here, this point ends up here, this point ends up here, this point ends up here. What happened to this whole thing? It got switched over like this. This whole piece flipped over here. This whole piece flipped over there. So when you take the Fourier transform, remember, of a Gaussian, you end up with that, right? And this is why. Because it has this butterfly structure in it. The reason they leave it in the butterfly structure is because it's part of the algorithm that makes it go fast. You don't want to shift it out of here. The reason it's going fast is because it has this structure to it. So you don't want to get down here, switch it back out, and then have to switch it back just to go back through the Fourier transform. This is what's making it fast. But this is also why you see this happening. It's related to this breaking up of the problem into smaller and smaller and smaller bits. And every time you do that, you have two problems. You're basically cutting a problem, the operation count in half every single time. Every single time. And then that gets you down to the n log n that you need. All right. We're not going to do much with this, partly, and that's why I figured it's something that if you want to learn more about, you can. You should at least be educated in the sense of knowing at least, if someone asks you what's the main idea behind a fast Fourier transform, you should at least be able to say, well, basically what the FFT does is it factors a problem of size n into a bunch of smaller problems and keeps breaking it down to you get n 1 by 1s. And this is why you get n log n. You should be able to say that. And here's how it does it. Now we're just going to use it. Hooray. Okay. All right. See you guys Wednesday.